Hello and welcome. Today we're diving deep into the cosmos, chasing a ghost, a particle so elusive, so mysterious, that for years it haunted the dreams of physicists. We're talking about the sterile neutrino, a hypothetical particle that promised to solve some of the biggest puzzles in physics, from dark matter to the very nature of the universe. But like many great mysteries, this one has a twist. Our story begins with the neutrino, a particle that's already famously shy. Trillions of them from the sun are passing through your body every second, yet they barely interact with anything. For decades, we thought we had them figured out. The standard model of particle physics, our best theory of the fundamental forces in particles, described three types, or flavors, of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. These particles are incredibly light, almost massless, and they can change from one flavor to another as they travel, a phenomenon called neutrino oscillation. This discovery was a huge deal, earning a Nobel Prize and proving that neutrinos do have mass, something the original standard model didn't account for. But then, strange things started happening. Experiments in the 1990s, like the liquid scintillator neutrino detector, or LSND at Los Alamos National Laboratory, saw something peculiar. They detected more electron neutrinos than they expected. It was as if a fourth, unknown type of neutrino was appearing in their detectors. This wasn't just a small anomaly. It was a persistent signal that hinted at something new, something beyond our established understanding. How could a fourth neutrino explain this? The idea was that this new neutrino would be even stranger than its siblings. It wouldn't interact through the weak nuclear force, which is how the other three neutrinos talk to the rest of the particle world. It would be a true ghost, only interacting through gravity. It would be sterile. This hypothetical particle was named the sterile neutrino. The existence of a sterile neutrino would be revolutionary. If it existed and had the right mass, it could be a candidate for dark matter, the mysterious substance that makes up about 27% of the universe but does not emit or reflect any light. The sterile neutrino could also explain why regular neutrinos have such a tiny mass through a mechanism known as the seesaw mechanism. The idea is that for every light particle there's a very heavy partner. Our known light neutrinos would be one side of the seesaw, and the heavy sterile neutrino would be the other, pushing them down to their tiny masses. The LSND results were tantalizing, but science demands reproducibility, so, in the early 2000s, another experiment called Mini-BUNE at Fermilab was built to check them. Mini-BUNE was designed to be more precise, to either confirm the LSND anomaly or put it to rest. And for years, the results were ambiguous. Mini-BUNE saw an excess of events similar to LSND, but not exactly in the way they expected. The plot thickened. The ghost was still in the machine, and the physics community was buzzing with excitement and debate. Was this the dawn of a new era in physics? The possibility of a sterile neutrino spurred a global race. Dozens of experiments around the world were designed or repurposed to hunt for this phantom particle. They used different methods. Some looked for the disappearance of known neutrinos, figuring if they were oscillating into sterile neutrinos, they would simply vanish from the detectors. Others, like Mini-BUNE, looked for the appearance of electron or muon neutrinos where they shouldn't be. Reactors, particle accelerators, even radioactive sources were all employed in this grand cosmic detective story. These experiments were marvels of modern engineering. They involved massive detectors, filled with tons of liquid scintillator or argon, buried deep underground to shield them from cosmic rays and other background noise. Scientists had to account for every possible interaction, every potential source of error. The stakes were incredibly high. Confirming the sterile neutrino would mean a Nobel Prize and a rewriting of physics textbooks. Failing to find it would mean something else was going on, or that the original anomalies were just statistical flukes or misunderstood experimental effects. For years, the evidence was a mixed bag. Some experiments reported hints of a signal, while others found nothing, setting stricter and stricter limits on where this particle could be hiding. The sterile neutrino seemed to play a game of cosmic hide-and-seek. Every time physicists thought they had it cornered, it would slip through their fingers. The proposed mass and mixing properties of the sterile neutrino kept shifting as new data came in. It was a frustrating, yet exhilarating, time for neutrino physicists. The data was telling a complicated story, and no one was quite sure how to read it. The turning point came from a new generation of ultra-precise experiments. One of the key players was the Micro-BUNE experiment, also located at Fermilab, sitting in the same neutrino beam as Mini-BUNE. Micro-BUNE was different. It used a liquid argon time projection chamber, a technology that gives you a stunning high-resolution 3D picture of particle interactions. It could tell the difference between an electron and a photon, a single particle of light, with unprecedented accuracy. This was crucial because the excess events seen by Mini-BUNE looked like they were caused by electrons. But what if they weren't? What if they were actually caused by photons that were being misidentified as electrons? If the excess was real sterile neutrino oscillations, it had to be electrons. If it was photons, then it was likely a known, just poorly understood, background process from standard physics. After years of meticulous data collection and analysis, the Micro-BUNE collaboration released their flagship results in 2021. The scientific community held its breath, and the result was a bombshell. Microbuoni's data showed, with high confidence, that the excess of events seen by mini-buoni was not made of electrons. The analysis strongly pointed towards the events being photons, produced from standard neutrino interactions that had been underestimated in previous experiments. In one fell swoop, the primary evidence for the light sterile neutrino that had puzzled physicists for over 2 decades had evaporated. The ghost that had haunted Fermilab's neutrino beam was, most likely, just a misunderstanding of the background. It wasn't a new particle. It was a tricky signature from the physics we already knew. The microbuoni result was a major blow to the sterile neutrino hypothesis, at least in the form that would explain the LSND and mini-buoni anomalies. Many other experiments from around the world, from reactor experiments in France and China to radioactive source experiments in Russia, had also come up empty-handed in their own searches. A global consensus began to form. The sterile neutrino, the one that was supposed to be just around the corner, simply wasn't there. So, is this the end of the story? Not quite. Science is never that simple. While the specific sterile neutrino that was hunted for decades appears to be a phantom, the story highlights something beautiful about the scientific process. It's a self-correcting mechanism. An anomaly appears. A bold new hypothesis is proposed to explain it. A generation of scientists dedicates their careers to testing that hypothesis with ever more ingenious experiments, and in the end, the data has the final say. The non-discovery of the sterile neutrino is not a failure. It's a triumph of the scientific method. We now understand neutrino interactions better than ever before. We have pushed the boundaries of technology and analysis. We have ruled out a significant piece of the puzzle, which in itself is a valuable piece of knowledge. It tells us where not to look, allowing us to focus our efforts elsewhere in the search for new physics. And the quest continues. The standard model is still incomplete. We still don't know what dark matter is. We still don't know why neutrinos have mass. The anomalies that started this whole saga, even if they weren't new physics, pushed us to build better tools and ask deeper questions. Perhaps heavier sterile neutrinos exist, hiding at energy scales we can't yet reach. Or maybe the solution to these cosmic puzzles lies in a completely different direction. The story of the sterile neutrino is a perfect example of how science works at its best. It's a tale of curiosity, creativity, and rigorous skepticism. It's a reminder that nature doesn't always give us the answers we expect, or even the ones we want. But the pursuit itself, the journey of chasing ghosts and questioning everything, is what drives humanity's understanding of the universe forward. The sterile neutrino may not have been there, but the search for it has left us richer, wiser, and better prepared for the next great cosmic mystery. Thank you for joining me on this journey into the world of particle physics. If you enjoyed this exploration, please consider liking the video and subscribing to the channel for more stories from the frontiers of science. See you next time.